Hello, my name is Samuel Breslin. I'm the Solar Gators or electrical integration lead. This is a video lecture about the low voltage power circuitry on our PCBs or printed circuit boards, which we design in-house. So before I go any further, I'd like to mention that the design that I'm about to walk through today was created by our electrical project manager, Mathew Shen. Um, so before we begin to design anything, we need to discuss the design specifications for this element um, of the overall PCB design. So right now I've got an empty project with just a power schematic. So you can go ahead and create this an empty project and create a schematic and go ahead and I named it power, but you can whatever you like. So as far as the specification goes, I'm going to go ahead and write them down in some text. So you can either click on the text up here, or you can hit P and text string. So the most important specification of this design is going to be our output voltage. So all of the electronics, or almost all the electronics on our circuit boards run off of 3.3 volts. So our power section output is going to be 3.3 volts output. Cool. Now after that, we want to be able to output a certain amount of current. So our boards really never draw more than 500 milliamps, and usually they don't even get close to that. But we're going to go ahead and put that as our specification. Output current. Oops. Okay, so now let me define the outputs that we want. We should define the input that we want. So our car runs off of usually two different battery sources. There's the main battery circuit, which operates at around 100 volts. This is fed through the power board, which steps it down to a steady 12 volts. So that is our sort of nominal power input. Although sometimes the car's auxiliary systems will be running off the supplemental battery. This is a small lead acid battery that sits in the side of the car. So this can be, and so because this is a lead acid battery, sometimes that voltage is going to dip as low as say 9 volts or go all the way up to 14 volts. So we want to be able to have a range of input voltages, I'm going to say from 9 to 14 volts. Nominally, of course, it's 12 volts. Input. And lastly, we want this to be quite a high efficiency design. This is Solar Gators. Everything we design has to be extremely efficient. Okay, so there are a couple main ways to go ahead and achieve these specifications here of these outputs and this input. And there's really two main ways. The first one that I'm going to look at is the linear regulator. So a linear regulator power supply is usually based around, of course, a linear regulator IC. And so these are going to be good for a number of reasons. They're usually going to be very cheap. They're going to be very easy to design around. And the downside of them is that they're going to take up a small footprint on PCB. So that's another upside. The downside is their efficiency. So a well-designed linear regulator circuit is usually going to have around a 60% efficiency. So not great Okay, that's the linear regulator. The other option is going to be a switching power supply. So this is going to be slightly more expensive, so not very cheap. Not as easy to design around. It's going to be slightly more complex. A slightly larger footprint on the PCB. There's going to be more parts around this linear regulator. The footprint of the IC itself might be smaller, but there's going to be more parts that you need surrounding it to make it work right. But the large upside is that a well-designed linear regulator can have over 90% efficiency, plus 90% efficiency. So very high in efficiency. So in the past, Solar Gators has used both these types of power supplies, but the one that I'm going to be discussing today is a switching power supply, mostly because of its efficiency. So there are a couple different types of switching power supplies. The first one, or the main one that we're going to be talking about today, is called a buck converter, which is a step-down power supply. So it's going to be stepping down the voltage, the input voltage, to a lower output voltage. There are also boost converters, which go to a higher voltage, and buck boost converters, which can do both. Okay. So now that we know we're looking for a buck converter with these characteristics, we can go to a website like DigiKey. Buck converter. DC-DC switching regulators. And we can use all of these search parameters, some of which we've defined already, like our input voltage, output voltage, to sort of narrow down the search for what we're looking for. For Solar Gators, we have a TI part sponsorship, so we like to use Texas Instrument parts. I've already chosen the part which we're going to be using today that we use on all of our boards, and that is the TPS. That is the TPS 629210. It's a 3 volts to 17 volts automatic OIQ buck converter. Okay, so now that we know the part that we're going to use, we can go back to Altium. We have our blank PCB, and we're going to go ahead and add our buck converter IC onto the empty schematic. So we're going to go to panels. I am making this project inside of the Solar Gators Altium 360 space, so I have access to all of our parts. And we can go to TPS, go ahead and look that up. And we have our TPS 629210. And I'm going to go ahead and add that to the schematic. Okay, so here's our schematic symbol. And I'm going to go pin by pin, explaining how we wire up this buck converter. So the first thing I'm going to do is go ahead and give us a label of IC1. Cool. And I'm going to sort of create a ground plane down here. Okay, so here's our pin 1. It is feedback / voltage set. So there's sort of 2 ways to use this pin. We're going to go ahead and go to the schematic and look at that. Look up VSet. Okay, so this is dependent on the device configuration. We can either use it as a voltage feedback input, connecting a voltage divider. If you want to learn more about this, there's a couple of videos in the description that you can look at. I'll talk more about those at the end of the video. But we're going to be using the VSet output. And by connecting a certain valued resistor to ground, we can choose the output voltage according to table 8.2. Let's go to this table. Now, as we defined earlier, we want a 3.3 volt output voltage. So you want to use a 249,000 ohm resistor. So I'm going to go ahead and go back to components, look up 249, and get our 249 kiloohm 0402 thin film resistor. So if you don't know what 0402 means, that describes the footprint of the resistor. So a lot of resistors, capacitors, those smaller parts, have predefined sort of standard footprints. One of those is 0402. So I'll go ahead and place it rotate it by hitting spacebar, place it down, and connect up the resistor. Go ahead and move this all up by selecting it and dragging it up. And connect up this resistor. Go ahead and rename this resistor 1. Okay, so there is our voltage set output. The next one is the power good pin, or PG pin 2. Sorry, I lost my notes here. Okay, before we move on to the PG pin, I'm going to go ahead and place what's known as a net label. So to place a net label, you can hit P and N as the sort of keyboard shortcut. I'm going to go ahead and place it with this little red star being on the corner there. And I'm going to go ahead and call this VSET. So I'm going to explain what a net label is before I move on. So a net label is a way of telling Altium in your schematics that you want 2 points in a schematic to be wired together. So to give you a better example of this, I'm going to go over to a different project of mine. You can go, this is for the front VCU that I'm actually going to be showing you guys how to design later. But you can see here, for example, we have the I2C lines here of this small memory chip, but it would be kind of cumbersome if we wanted to route these all the way over to our microcontroller here and wire them right to here. So instead we use these net labels, which tells Altium that when we take this schematic and turn it into a PCB design, that we want those 2 points to be connected. So I'll show you the PCB design. Now this is the main use of net labels, but there is one other sort of smaller use, and this is essentially sort of good practice. So without this net label, Altium doesn't really know what this sort of wire should be called when you go to route things up in your PCB design. But if you add a net label, even if it's not connected to anything else, Altium is going to label the lines for you, right? So it's going to call this NCW or NWC, even if you don't have another net label on the other side. It's going to go ahead and label this for you instead of choosing some sort of random name for it. So that's net labels. So yeah, now I'll move on to PG, or the power good pin. So the power good pin is pretty simple. The power good pin is a feature that indicates whether the output voltage of the buck converter has reached its target. So I'm going to go ahead and go to the data sheet. I believe it's on page 4. Is this chart, which sort of describes the function of all the pins. So it's an open drain power good output. See if we can find more information on that. Okay, here we go. Feature indicate that the output voltage has been reached and the device is ready. The power good signal can be used for startup sequencing, and the power good pin, this is the most important part, requires a pull-up resistor to any voltage up to the recommended input voltage level. Okay, so we're going to go ahead and do that. Now, there's a couple special types of net labels before we do that, we're going to discuss a couple special types of net labels in Altium, and they are sort of our power net labels, which you can access up here. They're called power ports, and you have all these different power ports for ground, VCC, at different voltages, and I'm going to create a plus 3.3 volts power port. And so anywhere this power port is located means that you want 3.3 volts connected there. So for some reason my descriptions are hidden, so I'm going to go ahead and right click on, select this part, then right click on it, sorry, double click on it, and unhide the label, and I'm going to name it plus 3V3 volts, capital V. The standard sort of writing would be 0.3 volts, but sometimes you can't really see that dot on an Altium schematic, so we like to do 0.3 V3 volts. Okay, so there is our plus 3.3 volts, and we want our power good pin to sort of be connected to that. I'm going to move that up. And we're going to make this a little prettier in a moment. Okay, so there's our power good pin. Yeah, so this power good pin will go low when the device is turned off due to, say, the enable going low, or some sort of under voltage lockout, or some sort of thermal shutdown. And that's pretty much it for that. I'm going to go ahead and add a net label for power good, PG. Okay, reset, PG. That all looks good. And like I said, I'll make this a little nicer looking in a moment. Okay, so now we have pin 3, our VOS, or output voltage sense pin. So this, according to the data sheet, let's go see what it wants. So let's go to VOS. And like I said, it's always great to design directly from the data sheet to make sure you're doing everything correctly. This is our output voltage sense pin. Connect directly to the positive output of the output capacitor. So we're going to go ahead and deal with the output capacitor and such in a moment, but for now, you can just go ahead and connect that up to our 3.3 volts. Okay, so that's great. The last pin on this side of the IC is the SW, or switch pin. This represents the sort of the voltage output of the buck regulator. This pin is not sort of a constant output voltage that we want, the 3.3 volts. Instead, it varies with the switching frequency and the duty cycle, and thus some filtering is required. To achieve this filtering, we're going to use an inductor and a capacitor. So for the inductor, we have a sponsorship from a company known as Coilcraft, and we'll be using a 2.2 microhenry inductor from that company. And for the capacitor, using a 22 microfarad capacitor. I might have misspoke. The inductor is a 2.2 microhenry inductor, not microfarad. So I'm not going to go into the math behind sizing these components. However, there's a lot of information regarding this in the datasheet, and I've also linked to Phil's lab video regarding this topic of sizing buck converter parts. Yeah, so I'm going to go ahead and get these components from the Gators library. Go to panels, components, 2.2 microhenries. So like I said, this is the inductor from Coilcraft, and we're going to move some of this stuff. Okay, this is our switching regulator, and for our capacitor, I'm going to go ahead and get a 22 microfarad capacitor. Right click, place, hit W to rotate, and go ahead and place that capacitor. Oh, that was a mistake. Components. Okay, let's go ahead and place that capacitor. We're going to go ahead and want to connect that capacitor up to here. And so this point here between the inductor and the capacitor, that is going to be where we want our 3.3 volts output. So that is perfect. Like I said, our VOS is supposed to also be connected to that 3.3 volts sort of output. believe I may have made a mistake. Okay, so let me review. VOS is connected directly to the 3.3 volts output, and yes, okay. I apologize. I did make a mistake with the PG pin, so we're going to go back to power good. Good. And like I said, this specifies that requires a pull-up resistor to any voltage up to the recommended input voltage. So we're going to go ahead and place a 100K resistor as an output, as a pull-up resistor, 100K. We're going to go with an 0402 resistor, and I'm going to connect it up again to our 3.3 volts output. Okay, so name this R2 and L1. Cool. And this will be C1. So this is the sort of output side of our buck converter. Let's go ahead and take a look at this for the reference I've been going off of, make it a little nicer looking. Okay. So to make it a little nicer looking, I'm going to pull this right down to here, and I'm going to move all of this out here, place that right there. Okay, that looks great to me. It looks like it matches up to our sort of reference schematic. I'll place the ground node right here. And I'm just going to move this resistor down. I don't like it sitting. I don't like it sitting on top of the wire. Okay, so we have PG, and it looks like we have in our reference, we have power, as sort of a prefix. Power underscore PG, power underscore V set. We have, we're not using one for VOS, and because that is, like I said, that is connected straight to 3.3 volts. And we have one for power switch, right? So this is not 3.3 volts right here because this is before our inductor. So this is two different nodes, but this, our VOS or voltage output sense, does not need one because it is on the same node. There are no components between it and 3.3 volts. So let's go ahead and place PN, oops, sorry, PN. We have our power switch. Okay, cool. So that is all for the output side of our buck converter. Okay, now to the input side. The first pin is quite self-explanatory. Ground gets routed to ground. Okay, the second pin, V in, it's also quite self-explanatory. That is our V in pin. We're going to go ahead and label that PN power V in. Awesome. So I'm just going to go ahead and route that out. And we have enable. Enable, let's go ahead and see what the documentation says about that on page 4. Enable. Enable disable pin includes a threshold comparator. Connect to logic low to disable the device and pull high to enable the device. We always want this pulled high to enable the device. So I'm going to go ahead and just attach it right to power VN. So as long as there's power on the device, the buck converter will turn on. The last one is the mode S or sconfig pin. So there is some important information about that in the data sheet on page 12. So this is the, oops, my bad, 12. This is the mode/sconfig pin. So there are a couple modes sort of that you can place it in. The mode that we want is for it to be VSET, right? That's what we discussed earlier with the output settings. We want it to be up to 2.5 megahertz switching frequency in order to maximize the efficiency. We do not want output discharge, and we're going to use auto PFM or /PWM. And so that means that we want to use a 42.2K resistor. So I'm going to go ahead and go panels, components, 42.2, and place that resistor. Go ahead and place it right here. And according to the data sheet, it needs to be placed between, I believe it needs to be placed between that pin and ground. So I will go ahead and route that. And name this R2, I believe. Oh, no, R3. Another Altium sort of tip, if you have a multiple schematic labels that are the same, it will give you sort of a red line along the component, indicating that you might need to increment to the part label. Okay, so there is the input side. Now, the last thing that we are going to be discussing today is that we need a sort of input filtering capacitor. So I'm going to go ahead and go to panels, components, and I'm going to get a 10 microfarad capacitor, and I'm going to choose, I'm going to expand this a little bit, and it's a little bit important which one we choose. I believe I'll choose this one. Okay, yep. Okay, so now when you're choosing these sort of power filtering capacitors, it's quite important to pay attention to their voltage rating. So you can see, I'm going to change that up a little bit. I don't like that. Perfect. I think I like that better. Okay. So if you click here, you'll see this one has a 50 volts rating and this one has a, sorry. This one has a 25 volts rating. So obviously this one is only really ever going to be seeing a 3.3 volts DC load, and this one's really only ever going to be seeing a 12 volts DC load. So why are we choosing capacitors with such high voltage ratings? That is because of something called DC bias. So when a true DC voltage is placed across the capacitor, it's going to decrease the effective capacitance of that capacitor. I'm not going to go into much on why. You can do your own research on that. But it basically means that we want to choose capacitors with much higher voltage ratings in order to sort of mitigate that effect. So yeah, so that is it for our buck converter design. Let's make sure everything matches up. We have all we really need to add is our power config net label, and everything else looks good to me. So PN power config. There we go. Now, in the next video, we're going to take a look at a few extra parts for this power section. One is going to be sort of a status LED. The other part is going to be choosing between two input sources, and as well as reverse polarity protection. And then after that, we're going to go ahead and get into routing this power section up. Routing there are sort of two difficult domains to route. One is high, power stuff like this, as well as high frequency stuff. And this is a switching power supply, so it sort of has both of those. So I'm gonna go ahead and save this, and that's it for this video.